Okay, so I didn't say last time I meant to. I've started following this paper relatively closely. So this is work with Artem Kotelsky and Claudius Zabrovius, who is here. And last time, lecture 2 was largely focused on section 4. So if, you know, you felt like you didn't get it all written down and you don't feel like looking through the video, it is written down. I'm trying to stay relatively close to these conventions. And then lecture 4. No. Lecture 4, mod 2. And then today, in fact, in some sense, you could try and just not worry too much about what happened last time, and we'll restart just from an algebraic point of view today. And this is today's lecture. I guess I really want to be done. And OK, so what did we learn last time? That there's an algebra, which we'll denote by B, which has two idempotents. A pair of operations, well, 2 times a pair of operations, D, relations that if I compose a dot or a dot with a saddle, then that moves the dot onto the starred component, so that has to be 0. So this is my algebra B, and that's somehow what we spent 90 minutes on last time, was showing that Barnotan's category from the right perspective can be completely captured with this information. So just to summarize, we had, this is another thing that I wanted to say. So I decided that I would write explicit exercises for the first lecture because I wanted also for people to have all these references for the different tangents you could go on. But for the remainder, I'm keeping examples show up, but examples are different than exercises. This is just a cultural, I'll try, I'm not claiming that my Blackboard work is easy to read, but X and X are different objects, right? So this is an example of something, and this is something you're meant to do in tutorial and ask me about, or ask Claudius about if you find us, and we're happy to try and answer. Okay? Okay. So some summarizing examples from last time were that our running example was that if I take a single crossing tangle, that this could be expressed as, let me just put all of the information in a curly bracket, as a chain complex of a certain sort, which we interpreted, where the map itself is the saddle coordinate. In a sense, this is exactly the same drawing that Daniel started his lectures with. I mean, there's the absence of the zip. There's an absence of orientation, which I'm still avoiding. But we're trying to change pictures into algebra in a rigorous way that can be manageable. OK. And the other example, but this has an exercise in it implicitly that I'm sure many of you did just because it jumped right out at you. But so I recalculated this, and it had these 4 vertices, just to give an example of what a general complex for a tangle should. And then I told you about de-looping and made some suggestions about simplification that I'll come back to today. Well, first you see a saddle. And then there'll be another object here. And this map is, because I want to write it here, well, what happens? It should be a sum. one sheet to another. From that, okay, so that's a linear combination in Cobb, and it is a map that runs from here to here. You can check that to 0 when you compose them together, and I'm claiming that it's a good exercise to here. You need to apply delooping. I guess it makes, equals is a little unjust because well, that's not the complex that I wrote last time. So I'm claiming that if you apply delooping and simplify, that is, you apply some Gaussian elimination, then you'll arrive at this more simple complex. And then we were looking at last time, and where this algebra came from, is that we could use this shorthand and just write the first as dot, dot. So two different style dots for these two different basic objects in the category. Those are my two idempotents. Okay, and then this second then would be dot, then S, the dot, and an open idempotent. I have this shorthand, and this shorthand is justified by an isomorphism. So there's an underlying isomorphism between this algebra and this full subcategory of Barnaton's category generated by the two simple tangles in this section that would be called small omega. It has a dependence on the star, and this equivalence here goes by the name big omega, but because of the dependence on the star, so there's actually, you can make 4 choices. There's 4 of these. I'll just put star because we made this choice of upper left. And so these now have some new notation. So by definition, to distinguish them from Barnaton's notation, I'm going to call these, so this is where you have to load your Cyrillic font package. This is Cyrillic D of marked tangle. Oops. And then Claudius asked me if I practiced. I swear I did. Here we go. Great.
What's the difference between the double bracket crossing and breeze?
The double bracket crossing and the Cyrillic D? Yeah, so that's what I'll talk about a little bit more today. I mean, there is no difference. These are flexible, though. They don't need to be delooped, right? So, but you can simplify them. That's Barnaton's theorem, and that's the reason Barnaton's so well is you can deloop everything, and you could express them as complexes only in the simple tangles. And if you're willing to apply Gaussian elimination, their claim is you can get down to something extremely simple. And we're going to denote these for the representatives that are using only this smaller subcategory, full subcategory, which we can rewrite in terms of B. But I think the longer answer and what I want to say is that these are complexes over categories, and these really are type D structures, or twisted complexes over B. So that's the next thing that I want to say. Does that help? So I'm just at this point it's just attempt to be careful, but in fact we're trying using the last 2 lectures is to show that this is really an intermediary object and that there's something else that we can study instead. Okay, so an important fact that this is bubbling up here is that this idea of a complex over a category So this is this. It's a Barnton, which we were looking at last time. This can be reinterpreted as a twisted complex. This is CF Amio's lectures. Or equivalently, we could use the language of type D structures and language from Both Heegaard Floer homology. And the fact is that these are equivalent. They're just different ways of thinking about the same algebraic object. Now, I did some hand-wringing in deciding whether or not I should introduce type D structures, and I decided that I'm going to. And the reason that I am going to is that, first of all, that is language that we're using in our paper. It's a matter of, second of all, I'm somewhat used to them because of Both Heegaard Floer homology. And because there are 2 lectures running in this school about Heegaard Floer homology, I think there are certainly some subset of you that will either are already or will be interested in looking at bordered Heegaard Floer homology. It is a part of the machinery that's extremely useful, so it's valuable to at least see where these come up. They really are just a just a chain complex, and I'm gonna try and explain that. Okay, so that's where we're at. And so the main thing is that these 2, so the Cyrillic D is for D structure. So these are type D structures. And to be a type D structure, there's always an underlying algebra. These are type D structures over B. Yep.
For what is the standard type D structure? We don't know about it.
I'm going to define them. Ask a question. An excellent suggestion. So this is the point at which you can, if you hated drawing all these cobordism pictures, you can just get back on the ride by saying, we're really just going to study this algebra. And in fact, you could just take that algebra as a black box and move it over to everything that you learned last week in Claire Amio's lectures and start taking it out for a ride using those tools. Okay, so let's let A be an algebra with I, its idempotence. The key examples for us, I'm not going to move away from these. Really, we're talking about B. That is the subject of this lecture series. But I think it is extremely valuable in trying to understand what all of you, and in particular, is moving between these, to consider the following categories / algebra, how you want to interpret the picture. So here's, as I said in tutorial to some of you, there is a ring that I am certain that you have spent some time with. You know some things about this ring, right? This is just a polynomials in H, give me the same H, over some field. Pick your favorite field. Mod 2 coefficients are fine. This I'm going to call R, to stay with the algebra notation. And it can be described as a quiver or as a category. This is a matter of taste. It has a single object, it is a single idempotent, and it has HOMs that are generated by a single arrow H. Right? OK, so up to how to interpret the picture, you can put in complexes over a category generated by that quiver, or a twisted complex in this setting. And actually, a lot of what you might relearn by running this through Claire Amio's machinery from last week are things that you have already proved in other settings, working through Dumbin and Foote or similar about this PID. OK? So great. Now let me tell you what a type D structure is. So over one of these algebras is, so this is a right type structure. This is a right I model V. That shouldn't be too scary. This is i.e. a K vector space that comes with a decomposition that looks like V, and then here I'm going to take idempotents in the ring. So take a bunch of basic idempotents, one for each of the vertices of this quiver, and write that as a sum over these, decompose that into pieces according to the idempotents. So in our B setting, we're going to have some vector space, and the elements, the generators of the vector space, are members of either the solid bullet or the open bullet. Okay, so there's just a vector space with a distinguished basis and a splitting. But where we're going to use this right action of I is that this comes with a delta. This plays the role of a differential, but it's a little bit funny. It's a differential that spits out copies of the algebra on the right-hand side. Okay, and it satisfies some compatibility. So that tensor makes sense over the idempotents. So this map well, I want to be able to apply it twice and see at 0. But really what the type D structure does is it splits out the process of applying del twice, and then the last step is it multiplies. And you're going to see that it's the fact that there are some zeros in the algebra that's giving you the that d squared is equal to 0. So first I'm going to apply delta. Then to apply it a second time, well, to apply delta a second time, there's a factor that I want to leave alone that got spat out by the first time. So on that component, I'll just apply the identity on the algebra. And then the last thing I do is apply the identity on the left component of V. That's composed with multiplication. So all of this should be 0. Right. So this is multiplication. In the algebra A. Okay, so I think the main thing to take away from this is here I'm just splitting, I'm singling out the role of multiplication M in the fact that I need d squared to be equal to 0 relation for a complex. So let me just do an example. That means that here is supposed to be a type D structure. So I have my Cyrillic D of marked tangle, 2 crossings. This is great. And I have a saddle, and I have a dot. And let me now call these generators something. So A, B, and C. Okay, so I have a vector space over K generated by A, B, and C. 3-dimensional vector space. I have the part, so this right action by the idempotent splits it into these 2 pieces. The dot, say, has K, is generated by a single thing called A here. And the open is K, B, C. So there's the underlying vector space with its splitting. And now what I really want to see is that if I apply del at A twice, I should get 0. But then I have to apply this big messy rule. Fine. Big messy rule looks like I'll drop the subscripts. Little d. Little del? Or little, wait, where? That's like meant to be the master, do whatever, like d squared equals 0 is like that's what you need a chain complex to satisfy. So that's d of the chain complex, right? We're working with the whole thing, like the whole landscape is homological algebra. So every object is a chain complex at some level, right? We have either a chain complex over a category or a twisted complex is a type of chain complex. And I'm saying a type D structure is a type of chain complex. So D is just whatever D squared equals 0 is the main thing we're requiring for something to be a chain complex. This is, I should put it in quotes. It's D in whatever setting you're in. So there is no other D on the, I don't know how to say it. Does that help? Okay, what is hell? Del is, I've just defined it. This is, well, I mean, okay. I'm going to finish the example. That's the point. Ready? Here we go. So that's the compatibility condition. That's meant to be 0. Right? The key thing is I am applying the thing that is meant to be playing the role of the differential in this setting twice. So I'm going to apply that to A, because that's where things are interesting. When I apply the first del to A, I'm going to get B. But on the right, I get a copy of something from the algebra, in this case, S. So I'm moving left to right in this directed graph that is representing this chain complex. And to this, I need to apply the remainder of the composite. Okay, so now I'm going to apply del to B and not do anything to S, which is going to move me along to C. And it's C tensored with D tensored with S. Okay, so what's happening? S. So this is me applying del, but I have to tensor it with the identity because there's this copy of the algebra right. That's kind of a mess, but I have the multiplication in the algebra, and that's really what does all the work. So there's what's getting fed in to. Now don't do anything to the element of the vector space C, but multiply D and S together. And so here I've gone, this is equal to that, equal to that, equal to C tensored with ds. Remember, these are written like function composition. This is perform a saddle, then concatenate onto the saddle the dot morphism. But we've checked that s times dot is 0. In fact, times dot from the strictly algebraic perspective is just stipulated to be 0. So this vanishes, and that means that here of gives me 0. And this diagram is meant to be showing you how d squared, the application of d twice, it just in this setting, d is called del, and it has this strange process for composing. But ultimately, you get something tensor 0. That, okay, yeah. The reason is because the example I'm starting with is just this directed graph. So, okay, what is that? Now I have to go back and try and interpret what it mean originally. So I've got something where the two different, these really are different idempotents. They represent the two different crossingless tangles. So the splitting is given to me here. I'm just reading it off. There are three, it's a three-dimensional vector space with some additional structure on it. And the first piece of structure is that some of the elements in the vector space are assigned to the left-hand idempotent, and two more are assigned to the right-hand idempotent. This is just a long-winded reiteration of what the directed graph is telling you. Yep.
Is this more than just business indicator and philosophy, the complex of modules over
No, it is a complex of modules over the algebra B, but in this twisted, in the sense defined by Claire-Amiot. So how are you going to do that? You either have to, yes, the answer is absolutely, but how do you make that precise? There's three ways to make that precise. One is to take B and view it as a category. That's a formal process. Take its matrix closure and so forth, and then take complexes over that, and then we're good to go. So. Yeah.
So this is just an invariant.
Yeah. Yeah.
And then this S is just an morphism.
Yeah. Yes, that was the content of Claire-Amiot's talk. So like so you're absolutely right. Yes, but to the vast majority of the people in the audience, that was a week's worth of work, and it was already blew their hair back. So, yes.
Type D
It is not a mess. Attitude is everything, people. Don't listen to. It's not a mess. It is exactly what you need to do if you want to manage the holomorphic curves that come up in the bordered setting that, sadly, you started with a closed Heegaard diagram. It was hard enough to do the analysis there. Right, Paolo? Then you pick a surface that projects a closed curve onto the Heegaard diagram. Then you're going to cut the Heegaard diagram into two pieces, and it starts bleeding out holomorphic information. It's not a good situation to be in. And the type D structure is going to be because it actually helps you to reconstruct the chain complex in a coherent way using a version of the A infinity tensor product. See, yes, you can do everything at this high level, but at the end of the day, this is something that gives you a way to compute. Now, I want to stress, it's absolutely a matter of taste and realizing, oh wow, this is helping me, pick my poison. These are all the same things, and I think it's super good exercise to fix this polynomial ring and step through and look at how they're equivalent. Because what's going to happen is at some level, if you really should be just building chain complexes over that polynomial ring, which is exactly the level of complexity that you were working in when you first worked through Hatcher's book. Okay? Your chain complex is over a PID, but then you can replace them in this setting, and that gives you a really good footing to move off to maybe more complicated algebras. Okay? So, walk before you run. That's my, yep.
Yeah, so this construction somewhat, if this construction is possible because of this strange key, you are implicitly saying that the chain complex associated to the two tangles are one-dimensional. While it's, as far as I understood before, there was something in abstract category and there was not really even vector space. I don't know exactly.
I think I kind of understand. Well, maybe I'll answer a completely different question. So let's pretend your question was, I just went to Emmanuel's lecture yesterday, and he said that the main philosophy should be that I should look for, I have this category that's describing cobordisms in the large with various decorations, and in order to work with those, I should look for functors out of that category into some algebraic category, right? Okay, now that's not what we're doing. So what I am proposing is a means of algebraizing Barnotan's category in the four-inner tangle case so that we have an algebraic model for the same thing. So we're not leaving. So yes, it looks like it's algebraic, but it's not algebraic in the sense that Emmanuel was looking for. It's just a model for working with these square complexes in a hands-on way. And then, in fact, last time, our time trying to understand the morphism spaces, and that got us some degree of control. Now I want to look at how well can we get our handle on the objects, again, without leaving the category. And the fundamental thing is that I find convenient. You could work with these pictures, but I heard some feedback that it was getting hard to take the notes with all the pictures from Luis. So, sorry. A suggestion. Other students had the suggestion. So this gives you a way of like a shorthand what these linear combinations of cobordisms are. Okay? And the wrinkle was that we had to mark a point, but we saw that points was really wrapped up in this whole mutation question anyway, so we're happy. Other questions? There is no little d. This is like a hot, this is in any chain complex. Yeah, that's my point. That's my point. This is not, it's like a funny model for a chain complex. This is, d squared is this process. And what it does is it's singling out, Claudius is so high, he's super right. Hold on a second. Claudius' comment might help. That I'm just applying d, I'm applying d again, and then singling out the role of the multiplication in d squared equals 0. So if you like, a type D structure is a notation heavy, extremely explicit way of showing what the role of the multiplication is in making d squared equals 0 for these chain complexes. That's how I think about it. That might be unhelpful to other people, but that's what we've done. D and D applied again. It's not 0 until the role of the multiplication is taken into account. Yeah, you could, that's true. You could try and build. Use this compatibility rate relation. I don't know. It's not really a third thing, but. I mean, what I'm trying to emphasize, you don't have to use these. I just think that people should see them if they're going to read about Both Heegaard Floer homology. So use to V tensor B over I into a differential module. Which is another to Emmanuel's question. All right. So it was foretold that I would spend a long time on this part of my notes. Yep. This eats three things. It takes in something in the vector space, and this needs to take in two elements. So luckily, the process from before had spit out two elements on the side of a vector space, and then, yeah. And you could, instead, if you don't like the extensor product, you write this C star of the list consisting of D comma S.
So to get out, the delta, little delta of the vertex was the next vertex, and then cancel the arrow. I guess this is right.
Yeah. Yeah.
But it's what happens if there are several arrows? Do you take some?
You need to take a sum, yeah. Like it's still like linear over K. It's still a linear map. It's a map in the sense of linear algebra.
But only, I mean,
There's going to be another example in a minute. So
when you always leave a question on the definition of this, we should figure it out. Can you just give us an example?
no, this is the no, Gregor. Actually, I did write down a definition, and yes, I gave you an example.
Delta was in this example. The 10 minutes figure out what the delta was. And from this kind of tricky. But maybe everybody has as much faster than I am.
Well, I mean, I don't know what to tell you. And I guess the reason I didn't write it down is it's the only thing it can be based on the discussion from all of last lecture. No, but that's what we spent all last lecture on. So I think that's what I'm cottoning onto your question, right? Because we still have this interpretation, right? I can still rewrite everything in this setting. Okay. So, yes, Paula. Yes, Emmanuel.
Just to be sure, there's no gain about thinking about type structure or thinking about D tensor B as a mutation model.
There's no. I really trying to emphasize this is strictly a matter of taste, and I'm hearing that these are leaving a bitter taste in people's mouths, but there is a lot of Heegaard Floer literature out there that will have these, so it's okay. Further questions? Like I said, this is the expected response to some degree, but you know, I find them to be quite tame. They do take some getting used to. So let me tell you some more. So you might be given maybe you have two type D structures. A morphism from, let's say, A to A prime will run actually from F. I should still see copies of, sorry, not D, copies of the algebra being sent out to one side of it. So to fit morphisms into this picture. And then we'd like to be able to form chain complexes. So compositions, how so this is really the reason people don't like them, is that these extra funny things happen. Yes, thanks. The prime here. And so then compositions, so if you, for A to A prime to A W prime, this will be G and this will be F. Well, those are also going to look funny, right? So here I'm going to first apply G, and then I'll have F, but there's an identity component that I have to ignore, and then after I've ignored that and composed, then I can apply the multiplication. So that's how, oops, my apologies, that in order to compose things together, because of this additional algebraic object that's jumping out on the right-hand side, we just have to compose with the multiplication in hand. OK, so again, G will send an algebra element out. F will send another algebra element out. That'll leave two algebra elements on the right, and I'll multiply them together, and that's the result of this one. Why am I telling you this? Well, one way to get sunk into how these are remixing the other two settings is you could now look at morphisms from D to D prime. And so this is a chain complex. And how is that going to be a chain complex? Well, I need some D. I'll use capital D because that's what we used in the paper here. So here I've got some F. How do I take D of F? Well, first I should apply F. So I'll write it out longhand, but this is F and then D. So how do I apply D after F? Del is the role of D, and then I have to multiply. And let me so with mod 2 coefficients, because here there would typically be a sign, and that will depend on the grading of F, because I'm going to move F past del. So I'm taking del composed F and F composed del. So identity and multiplication composed with F with identity composed with del. Okay, so that's something to unpack and check. So this really should look like this really is del F plus or minus with the sign F del, which for people who have thought about chain complexes built out of morphisms will look familiar. Okay, so that's something to work through. Okay, great. So the point of this is come back to this question of reassembly. From last time. And how is reassembly going to work? Well, I'll have a pair of tangles, and I need to glue them together. Now, we've made this choice of endpoint. So the way I'm going to rewire my stacking one on top of the next and wiring them together. To do that on the blackboard, I'll need this. Now, for people who have thought about Khovanov homology, what you're noticing is I have, due to the presence of the base point and the fact that I'm being very careful to make sure that that starred component is glued to the starred component, I also have a distinguished arc, right? As such, you should be expecting that everything is going to be reduced, right? So I could just cut that arc and send it off to infinity, and I'd be looking at 1, 1 knots. Okay, so that means I can put this all back in the tangle setting with non-empty boundary point. That's something we'll come back to in a moment when I talk about conventions a little bit. But what is the point? So now, we have the following. If it's the first time you're seeing it, this is a definition, but it's really a theorem because one of the two symbols has meaning already in the literature. So this is my knot K, and the following holds. If I want the Barnaton chain complex for my knot K, then that's the same as looking at the morphisms, type D morphisms of the type D structure for one tangle and the type D structure for the other tangle, with a funny wrinkle that I need to do something to one of the two entries. Let me say what that is in a minute, but the point is that this is KH, in fact, graded. Once I put the grading back in, this is as KH modules. It's my favorite ring showing, right? So this is good news. So we can put things back together. This here, this is just means, so M reverses arrows. In the given type D structure. It does something to grading as well, but okay. So it does reversing arrows and reinterprets that as a type D structure. And what you can check, if you like, by looking at the original definition on the left-hand side in Barnaton's setting, is that if I take M, apply angle, that's the same thing as applying a mirror operation to the tangle itself. And hence, what this is doing on the level of the type D structure is the same thing. It's just telling me that I should mirror the tangle. Why this has to be so, maybe will be, it feels a little more natural after I tell you a little bit more about these objects and how we're going to interpret this morphism. For now, what's happening is in Barnaton's category, if you look at Barnaton's original paper, he's going to state everything as a tensor product. And here we're restating everything as morphisms. And you know that if you move between morphisms and tensor products, you have to dualize something. This is dualizing one of the entries. It really is a tensor Hom duality happening here, which is mellow. It's just irritating to the convention. Questions? Yep.
How important is the fact that the diagrams like this? What's the role of the person drawing the code?
Well, I mean, it's important. You could pick any convention that glues it together so long as the stars are matched up.
It doesn't depend on.
The stars have to be matched up. I think that's the most important. I mean, you're going to have to change all of our proofs on some level if you change to a different diagram. But here, instead of putting them side by side and wiring them together, and then we don't know how to manage the star, this is us. You really should think of this as stacking one on top of the other. In fact, really what we want to do is understand how the two objects are communicating on the boundary. And so this is the first lining things up about some orientation. So how important? I mean, not important. This is a perfectly reasonable way to glue tangles together, but it is the way. Bad, terrible answer. Okay. Further questions? Yep. No, these are not chain complexes of KH modules. So this is like given to us as a chain complex of KH modules, but I haven't talked about it yet. And so if you haven't seen that, I'm saying, why don't we take this as your definition for something in the closed case? So this is something associated to a knot, whatever it is, and I'm saying that if you're taking this as a definition, you should change the homeomorphism to a colon equals. Or maybe I should have set up the homotopy because I could make other choices for the diagram case. I mean, let's say this. Other questions? I don't mind the questions. I hope I wasn't seeming acerbic. The coffee hasn't hit yet. All right. So it makes sense for me to pause now as that's digesting and tell you just a few conventions about Khovanov homology so we can line things up, find them. But in a certain sense, if you know these objects are out there, this is not an unreasonable definition. This is how things get calculated in nature, I guess. It is a restatement of Bayatan's results. So this is how his computer program works. It divides and conquers on tangles, and it computes a tensor products along the way. That's what we're restating here. Great. Think, you know what, a good exercise, better than that. That exercise is not enlightening. It's sort of part of it. But you might calculate and interpret so by interpret, I mean by following what I said here about tangles. So decide which tangle diagram this goes with. That chain complex. Okay, that's something you could do brute force, and that's assigned to two relatively simple tangles. So what knot is that, and does it check out? Okay, so awesome. So what is Khovanov homology, and what does this sequence of symbols C, B, and twiddle mean? So Khovanov homology, this is a K-vector space. KH twiddle assigned to a knot K with a bigrading. So that this is of a complex that looks like CKH twiddle I J. There's some differential here that is raising cohomological grading here. And I should have put K's. So we pick a diagram, and form a cube of resolutions, and then apply UFT to that. That comes from the saddles. And the splits and the merges in the different directions on the saddles. And there is a chain complex out there that does this. And the way I've normalized things is that if I take its graded Euler characteristic, so what is that? That's a sum over, we meant that u and v. I wonder if this will mess me up. Okay, so I have I and j. I'm going to take an alternating sum in the I and a t to the Jones grading j divided by 2, and then take the dimension of what I see in grading I and j, k. That's a polynomial in T, and this is exactly a polynomial, but this is normalized so that v of the unknot is 1. That means that the round circle has chain complex that's sitting of one dimension sitting in grading 0, 0. Okay, so that's not how to define Khovanov homology. That's what Khovanov homology is. Once you've picked a definition, calculated this vector space. Mainly, I want to tell you what the convention is, and then say in words, we're really working with the reduced theory. The reason it's natural to work with the reduced theory is we have points. So that orange edge is really telling us that we should be reduced. In fact, it's the reduced theory that's natural in this setting. Okay, so that's what Khovanov homology is. I want to have a running example. There is some sensitivity to the coefficients, so let me take k to be the field of 2 elements, and the knot, the other k, to be your favorite knot, the right-hand trefoil. And what will happen here is 2, 4, 6, 8, 0, 1, 2, 3. You'll get a copy of F, copy of F, and a copy of F. And how does this Euler characteristic work? Well, it's saying that each coefficient in the is obtained by taking a characteristic in a particular slice at that given height. I divide the grading by 2, so this is I, and this is j. I'm taking Euler characteristics horizontally. So here I have something in primary homological grading odd, so there's a minus sign, and t to the 8 divided by 2 is 4. So this one-dimensional group is sitting in grading 2 and even gradings. T cubed, 6 divided by 2 is 3. There's nothing multiplying the t squared entry. And then down here there's t, again, 0 is an even grading. And this is there's the Jones polynomial of the trefoil. Okay, so that's not telling you the definition, but I am telling you the grading normalizations that are happening here. Okay? Great. So now what is Barnaton homology? So now this is a graded KH module where grading of H is minus 2 in the second entry, so this is 3. So I get this is the homology of a complex of a graded complex of free KH modules denoted CBN. Okay, that checks out right here. are meant to be getting a graded KH module. And this is now giving you a hint of what the grading of D and S squared should be, because D and S squared conspire to give you H. Right, so both of those should have grading -2, appropriately interpreted. Okay, this, if I take CBN K and I specialize so that I want to specialize it with its differential specialized, right? So that's pretty good. Nope. This. So this is the Barnton differential here, but I'm going to set H equals 0. What should I recover? This gives me back CKH of K, but tensored with KH. So it's not far away. What this tells you in the end is that if you want to recover Khovanov homology, then you can from this object. This is telling you that I should take a cone on H, or maybe that's in quotes. So let me tell you what this of the Barnton homology and whatever the H map does on this Barnton homology. And I'm telling you this because structurally this should start to look a lot like HF minus. Okay? And sorry for not putting the gradings in, so let me sprinkle them in. I want to okay, so H, I have to shift things around because H has drops quantum grading by 2. Okay, so the moral of the story here is that you can drag CBN. Once you have CBN, you can take a cone on the H action and get the reduced Khovanov homology back out. Okay, so that's the structural landscape that we were trying to understand in the first place. Back to my example. So if I were to compute this Barnton homology, what you are saying is there's going to be a single tower, and this is all wrong. 2, 4, 6, 8, and then over grading 3, 8, there's a single copy of F. And this is secretly one of the truncated towers that you're seeing come up over and over again in Marco's lectures. This is FH, but I'm killing H. Now I want to just bring this back to your favorite type D structures. First thing I want to do is tell you the key theorem here, which collects work of Lee, Rasmussen, this more general homology theory that shows up in Barnton's paper as calculated by Turner. Well, that is that given a knot, one component, we'll have that the Barnton homology of K will have a single free sum, one single infinite tower, and then it'll have a bunch of H torsion pieces. So things that are of the form FH mod H, FH mod H squared, FH mod H cubed, and so on. I didn't say finite dimensional anywhere. These are finite dimensional, so that decomposition will stop at that point. Okay, and the best part is that the grading here, this is ingrading. So the primary grading will always be 0, and the secondary grading will be S. And it has a dependence on the field. So this S, this is Rasmussen's S invariant. And I just want to highlight that you get one invariant for each field K. These do differ in general, which is remarkable. It's for K. Sorry, thank you. This really is. I'm going to put my theorems general. Yeah, that's what the ... Okay. Fantastic. So the reason for doing the extra work to work with Barnaton is that you really want to find this value. And this gives you a module way to find it rather than a filtered spectral sequence calculation way of finding it. Again, that's a matter of taste, but that's the real reason that we want this object. Okay, so now just to observation. Where's their space? So here's some representative for the chain complex of CBN. 1, 2, 3, 2. We'll have a copy of, can I go back to my 2-element field? And then in 2, 6, and here I need a map called H. All right, I'll give that a name. That's CBN, and I've for my trefoil knot, and I've expressed it as a complex of free modules. So let me remind myself of that by writing a subscript R. On the other hand, I could instead express this same data as a type D structure over R. Okay, how would that look? So now there's one idempotent, so everything is just a vector space, but each of the elements of the vector space, I confusingly call them one thing, diamond, right? That's my single idempotent. And there's map here. So now let me try to make amends with Gregor. What is del here? Del of A is 0. Del of B is C tensored with H. And actually, del of C is also 0. And now you can check the compatibility works. Okay. This is a different notation too. So I'm going to call this CKH twiddle of the trefoil upper R to remind me that it's a type D structure. Okay, so different notation, same thing. And here is the cool thing, which is an exercise that's really for people who are looking at bordered Floer homology. So the exercise is sorting out what these symbols mean. So that is the following. If I want to recover CBN, I can get it, I can move back and forth between this type D structure view and this modules view by box tensoring with the algebra itself viewed as a bimodule over it. And symbolically, what box tensor products do is they pull things from upstairs to downstairs. So this is the first time we're seeing this. It's also the last time. In the interest of connecting the dots between these bordered Floer homology lectures and Floer homology lectures and what we're doing here, this is a first basic example for getting your hands dirty of bouncing between these two perspectives. Here it's really just a rewriting process, but it can be fit into this language. So if you're thinking about bordered Floer homology, I think this is a really great first exercise. Okay. Questions? So, Gaussian elimination. This is going to convert into a series of, but what I want to do is stick with the reason I came back down to this polynomial ring. I want to make a geometric observation that's near trivial, but I want to connect it to an algebraic observation that you have proved whenever you were last subjected to dumb or its equivalent. I don't know what people are using these days in courses about rings and modules, but so what is that? Well, the first thing is which in our paper shows up as the cancellation lemma. I'm just going to try a suggestive example. So suppose I have x, y, z, and w. And now these are meant to be type D structures over R. So the maps here will be and ones. I'm going to not decorate arrows that have ones on them, just for convenience. And I'm trying to be suggestive idea about grading. Grading that's running horizontally, and there's a quantum grading running vertically. Okay, so this is like I and I plus 1. This is j, j plus 2, j plus 4. Okay, so that's a small type structure, and I'm trying to slowly suggest that these can be graded, but it's a 4-dimensional type D structure, and it's got some very simple operations. So in particular, for instance, here's finally an example where there's two edges leaving something. So d of y, that's going to be z tensor idempotent, so I won't write it, plus w tensored with h. Del of w is 0, del of x is z tensor h, and so forth. Okay. Okay, so what I want to compare to is the complex that just has x and w and a single minus h squared. So again, now I'm just, I guess this should have extra layer in it. What happened? No, that's fine. That's good. Okay. I'm going to stop adding the dotted orange arrows. So how might you do this? Well, you could run in here by an identity. But if I do that, I think there's a problem. So I get something, I get this minus h squared. So actually, to get a reasonable chain map, I really should put a minus h right there. It's a chain map. But if you try to come back the other way, w, y, z, x. Well, not much to do. But again, here there's a minus h squared hitting this guy. So how can I get that as a composition? There's an h here. You do that by minus h. Okay, I'm going to call things something. So let me try and make sure I give them the same names as before. So this is G, and this is F. So I'm going to slowly write through what we were doing in Emmanuel's lectures and connect it to some notation that's ultimately I'm going to leave the proof in general as an exercise and tell you where to go and look at it. But this is, I think, the real working example. Because what we're trying to do is we're trying to get rid of the zigzag. Okay, so this is handy. You've seen this if you've tried to work with spectral sequence. We're going to try to kill this one, but that's going to induce a map that runs up by degree 4. Okay, so if you compose G, yep. This thing, e.g., like for this symbol. Not in this one. So, and that's not a delta. Sorry, that's a z, and that's a 1. And then I decreed that I'm going to stop putting 1s on. Well, I didn't, but I may stop putting 1s on edges. So there's 0 maps, no arrow. Undecorated arrows are 1s. So this is actually equal to the identity. So that's something you can check. But if you try and compare GF and subtract off the identity, that's going to leave something behind, right? So the identity is going to remove all of these. What's that? No. Really? You're right. I'm not a function composer. Okay, so first F, then G. This has a defect, right? So when I compose these together, I get things that look like, switch to green. For instance, Z goes to W, goes to W. So this has a minus H on it. And X goes to Y. So this also has a minus H on it. So that's a pretty big mess. So let me write it out again. So we've got W, Y, Z, X. And W, Y. x. And what's left over when I subtract the identity away is like this. This is the defect. I'm keeping it from being the identity. Minus h's. So that's z and minus h. Okay, so this is something we want to get rid of by a homology. And so that should be a backwards arrow. And I claim that you can do that by considering that homotopy, small h for homotopy, which is running from something in grading I plus 1 to something in grading I. You can check if we perform D and then H. Sorry, H should be something. No, that's just H is 1. So H and then 1 cancels this minus H. Yeah. That's right. Like something in grading I plus 1 backwards to something in grading I. So the same conventions as first day. Okay, so now you want to check that this defect is corrected by del H plus H del. Okay, so that's how cancellation works in general. Now you can go back and now look at the general setup. So work through proof of lemma 1, 6, 7 is the next one. And there things are a little more general. So the del is something that's internal to the algebra, and you should set that equal to 0 and run that proof with this setup. So the first thing to do is there's a z and a y1 and a y2, and they're together into a triangle. You should figure out what z and y2 are in this diagram. This is y1, this is y2, capital Y's, and there's an identity between them. You're trying to cancel that identity. And there will be an inverse. The inverse is also a map by 1 that runs from z to y. Okay? So this should look familiar to anybody that's thought about spectral sequences and canceling differentials. Right? We're canceling a differential and inducing a map. But this is really explicitly how it goes. Okay, so there's also cleanup. This is 2.17 in it's a little bit at least notationally easier. Let me just suggest some examples and then this will set me up for what I want to do next. So the examples, or maybe these are now not examples. These really now are exercises. I would like you to show that I'll write them as type D structures. So here's a type D structure you might see. And I claim that's not cleaned up because it has two things leaving from this lower idempotent. So again, I'm sticking with this convention where there's the gradings if you want to put them back in. This, I claim, is homotopy equivalent. It is possible to get up to homotopy, get rid of the h squared. Okay? So that's number one. And the other one that is important and instructive, let me put the box in because this one matters. So maybe I have something of, no, it's H. Thank you, Gregor. I'm going to have all H's. And I claim that it is possible to homotopy to write this instead as something with just two short length 1 segments instead of that box. Okay, just as a sanity check, the homology here, we're going back to the homology is the same, right? In the spectral sequence, we want that that gives me something cyclic. This is something acyclic. It feels like it should check out, but there's an explicit cleanup lemma. So the third exercise is to work through proof of lemma 2.17 in KWZ. Again, here I'd take delta equals 0 as the first passage. And then you can work back if you want to look at this general setup where the categories, the underlying categories are enriched over chain complexes, so there's internal differential. This is if you wanted to move from algebras to working over differential algebras. Okay, so great. As an algebraic summary, this is telling you I can restate. Yes. Yeah, get lazy because they're there for grading reasons. Because the arrows are going up in grading, they have to be H's. They can't be 1s. It wouldn't be graded. But yes, I should have put the H on them. So this wasn't planned, but it went pretty well. So here's this same theorem is that KH twiddle K thing. This will be in grading 0 SK. And then there'll be a bunch of little short complexes with H. Maybe there's N one of those, plus a bunch of little short complexes with H squareds on them. Maybe there's N two of those. And then this is keep going, but it's going to stop somewhere because everything is finite. So continuing with my tradition of overusing Ks, H, and there's N of those. Okay, so you have one thing that's isolated. Its grading is given by Rasmussen invariant. And what on earth is this? Well, clearly, I could have much more complicated ID structures in this simple setting, but after you apply cancellation and cleanup judiciously, you'll end up with something in this very simple form. This should look like the classification of modules over a PID. We just reproved it in a very strange way. Okay, so this What? Ye- Yeah. Okay. Is better than that. Okay, it's better than that. Thanks. I was trying to. Okay, thank you. So this thing, I removed the C, right? So this is a choice of representative. This is the fully canceled. Representative. CKH twiddle, and I ran out of space. I'm not going to put the K in there. And actually, this is funny, right? We didn't have this notation. It really is KH, K, upper R. I make a choice of representative that has this really, really nice form. Final thing I want to say is that this has a graphical representation. And that is carrot to get you coming back on Friday. Listening. It's the single idempotent. Remember that here I've got this ring R, which is just a polynomial ring in one element, and I want to represent that. I'm just trying to distinguish my diamond idempotent from my dot idempotent. It's just to remind us that we're in a different category. So that's the category, or the algebra, depending on your taste. So the last thing, coming back to this, is the following graphical representation. So this is just an annulus. I've put some funny marking on it. Funny marking is because there's this piece of the annulus that I would like to complicate next time. But that piece of the annulus, that edge is going to be assigned to the diamond. Two copies of it just because it's, I just labeled it twice. And there's a map that runs around following an orientation of this annulus that picks up an H. Okay, so type D structure in this setting. Suppose I want sorry. So this is the last gasp for this lecture, graphical representation. Which is here just a basic choice for how we want to repackage this restatement. Here I'm going to look at the fully canceled and cleaned up representative of the trefoil, which I know should have three generators. And here's a set of curves that represent what's going on. This is my thing in grading 0 and Rasmussen variant 2. And then there's something in grading 2, grading 2, 6, running down to something in grading 3, 8. And that's what I want to spend next time explaining. You're welcome.